Hello and good morning, dear students. Now we are solving problems on chapter number 2. So we are taking only solved problems. So problem number 1 we already solved in our previous lecture. Now we are starting with problem number 2. So problem number 2 I have written over here. Problem number 2 is a particle moves in a circular orbit under action of attractive force. Full stop, which is directed toward fixed point on a circle. Show that magnitude of force varies as fifth power of the distance. So here we are solving this second number problem. So what is given? Particle moves in a circular orbit in a such a way that attractive force is directed towards fixed point on the circle. So first of all, we have to draw a circle on which that particle is moving. Okay, so this is the circular orbit under which this particle is moving, and suppose we are taking fixed point over here, and if that particle is over here, then force is like this. Okay, suppose that particle is over here, then force is like this. Suppose that particle is over here, then force is like this. Okay, so here if a is radius of this circle and r is the distance between circle and that point, okay, fixed point, and m is the mass of that point which is moving in circular orbit. So diagrammatically we can show situation like this. Now we know that to find out law of force means we have to show that force varies as fifth power of the distance. So we have to use differential equation of motion. What is differential equation of motion? D2u by d theta square plus u is minus m divided by l square u square f of 1 over u. Okay, so here this is equation 1 and u is equal to 1 over r. So first of all, we have to find out equation of r in terms of theta. Now we have to define theta. So how we define theta? Suppose we choose our origin at fixed point, and if distance is r, and we can choose this angle as theta. Now here, if you draw this point, then we know that this is nothing but diameter of circle, okay, which is a which is 2a, and here this angle must be 90 degree. So if you take cosine of theta, so this is the hypotenuse which is 2a. Okay, so what is cos theta? So adjacent side is r divided by 2a. So r must be 2a cos theta. Okay, now what is u? U is 1 over r. So therefore u which is 1 over r, which is equal to 1 over 2a, 1 upon cos theta is sec theta. So this will become sec theta divided by 2a. So u which is 1 over r, and that is sec theta divided by 2a. Now we have to put this in equation 1. So for putting this in equation 1, we have to differentiate this with respect to theta first. Now differentiating with respect to theta, we get what is first order derivative? Du by d theta is equal to, so 1 upon 2a is constant, derivative of sec theta is sec theta tan theta. So again differentiating with respect to theta, we will get, so second order derivative d2u by d theta square is equal to 1 over 2a. Now sec theta tan theta, here we have to use product rule. So first of all, derivative of sec theta, derivative of sec theta is sec theta tan theta multiply by tan theta, so that will become tan square theta plus sec theta into derivative of tan theta, which is sec square theta, so that will become sec cube theta. So you can take sec theta common from this, so sec theta divided by 2a in bracket 1 plus tan square theta. if you take sec theta common, so that will become tan square theta plus sec square theta. Okay. Now call this as equation 2. So put equation 2 in 1. What we will get? d2u by d theta square. So that is sec theta divided by 2a. Here sec square theta plus tan square theta, okay, plus u, and u is what? Sec theta divided by 2a is equal to minus m upon l square u square f of 1 over u. So if you solve this, so base is same, so we can take again here divided by 2a common. Okay. Now in this equation, if you simplify this equation, on the left hand side we get sec cube theta plus sec theta tan square theta divided by 2a, okay, plus sec theta, and on the right hand side what we will have? Minus m l square u square f of 1 over u. Now from this sec theta and sec theta, if you take sec theta common, okay, so that will become tan square theta plus 1. So again, using identity, 1 plus tan square theta is equal to sec square theta. So 1 plus tan square theta is equal to what? Sec square theta. If you use this identity in this equation, here again we get this sec square and this sec, you will get sec cube theta. Now this sec cube theta plus this sec cube theta, so that will become 2 times sec cube theta. Now remember, u is what? U is what? 1 upon 2a into sec theta. Okay. And here what we have? Here we have sec cube theta. Okay. If you take u cube, so that will become 1 upon 2a cube into sec cube theta. So sec cube theta upon 2a. So if you take this 2a and here you will get 2a square. So 1 upon 2a sec cube theta is nothing but 2a square u cube. So we can put this in above equation. So here you will get u cube multiply by 2a square, okay, into 2 is equal to, on the right hand side, is equal to minus m l square u square f of 1 over u, and f of 1 over u is equal to this 2 into 2a square u raised to 5, okay, divided by m and l square. So all this term is constant. See, 2 is constant, 2a square is constant, l is constant, m is constant, and u raised to 5. So negative sign means force is attractive, and if you put value of u as 1 over r, so that is nothing but 1 upon r raised to 5. So we can say f of 1 over u is proportional to minus 1 over r raised to 5. So force is reciprocal of fifth power of the distance. So in this way we have solved problem number 2. Now we are moving to problem number 3. So what is problem number 3? A particle moves in an elliptical orbit about gravitational force center at one focus, full stop, if greater and least speeds are v1 and v2 respectively, show that eccentricity E is v1 minus v2 divided by v1 plus v2. So here we are using Kepler's law of planetary motion. So we know that from first law, every planet moves around sun in elliptical orbit. So we can draw that like this. So suppose this is the ellipse. Here we have one of the focus, and here we have another focus. Suppose sun is situated over here and planet is moving like this. Suppose this distance is r1, which is least speed, and this distance is r2, which is maximum speed. Suppose here velocity is v1 and here velocity is v2. Okay, now this distance is r2, this distance is r1, velocity v1, velocity v2, and mass of planet is m, which is reduced mass of planet and that sun. Now from equations of conic section, we know that L upon R is equal to 1 plus E cos theta. So at R is equal to R1, theta is equal to 0. So what does it mean? So if you put value of R is equal to R1, theta is equal to 0, means we are over here. Okay, R is distance between sun and planet. Suppose that planet is over here, then R is this. Suppose it is over here, then R is this. Means if when planet is over here at R is equal to R1, angle between this radial vector and position of that planet is 0. So from this equation we get L upon R1 is equal to 1 plus, if you put theta is equal to 0, we get 1 plus E. Okay. Similarly, at R is equal to R2, so this distance is minimum distance and this distance is maximum distance. When that planet is over here, if you draw vector R and position of that planet, so angle between this position and this is nothing but 180 degree. So that we already discussed how that angle is 180 degree. So at that time, so this is maximum distance. Okay. Now, if you put that in this equation, so what you will get, L upon R2 is equal to 1 minus E, because if you put value of theta as 180 degree, so cos of 180 become minus 1. So this is equation 1, this is equation 2. Okay. Now, suppose this point is A and this point is B, then we can say from point A and point B, what we can say, angular momentum at A must be equal to angular momentum at B. Why? Because angular momentum at every point during planetary motion is conserved. So angular momentum at point A is equal to angular momentum at point B. So what is angular momentum? mv into r. So angular momentum is nothing but r cross p, and p is what? Momentum, linear momentum, which is mass into velocity. So angular momentum at A is what? Mass at A, velocity at A, r at A is equal to mass at B, velocity at B, and distance at B. Now see, mass at A is m, velocity at A is v2, okay, and distance at A is r2. Again, mass of reduced mass at B is m, velocity at B is v1, and distance is r1. So this m1 will get cancelled. So we get v2 r2 is equal to v1 r1. So from this equation we can say v1 upon v2 is equal to, if you take this v2 on the right hand side, r2 upon r1. So V1 upon V2 is equal to R2 upon R1. Since R2 is greater than R1, see, R2 is this distance and R1 is this distance. If you take R2 divided by R1, so this distance is greater than this distance. So this must be, if R2 is greater than R1, so this is greater than 1, which means V1 is greater than V2. So V1 is the velocity at point B and V2 is the velocity at point A. This distance is this point is known as perigee and this point is known as apogee. So velocity at minimum distance is maximum and velocity at maximum distance is minimum. Okay, so that we can prove over here. Now to get equation for eccentricity, we know that v1 upon v2 is r2 divided by r1, and from equation 1 and 2 we have this equation for r2 and r1. Okay, so let r1 is what, r1 is what, l divided by 1 plus e, and r2 is what, r2 is what, l divided by 1 minus e. Okay, so put in equation 3. So what you will get, v1 upon v2 is equal to, v1 upon v2 is equal to r2 divided by r1. So l divided by 1 minus e divided by r1, which is l divided by 1 plus e. So this l will get cancelled. If you do cross multiplication of this equation, so v2 into 1 plus e is equal to, v2 into 1 plus e is equal to v1 into 1 minus e. So v2 plus v2e is equal to v1 minus v1e. Okay, so if you take this term on left hand side and this term on right hand side, so v2 plus v1 multiply by e, okay, is equal to, if you take this v2 on right hand side, so v1 minus v2. So from this equation we can say eccentricity e is equal to v1 minus v2, okay, divided by v1 plus v2. So this is the required answer of problem number 3. Now we are solving next problem, which is problem number 4. Show that product of maximum and minimum linear speeds of particle moving elliptical orbit is 2 pi a divided by tau its square. So here a is the semi-major axis, tau is the periodic time. Now if you have to solve problem number 4, again we know that from Kepler's law every planet moves in elliptical orbit. So again at perigee and apogee we get these equations. Okay, so here up to here we can use same equations that we did for first problem. Now angular momentum at A is what, m v1 r1, and angular momentum at B is m v2 r2. Okay, so here I think this is at B and this is at A. Now L square is what, if you take product of this, so this is nothing but LA into LB. Since LA is equal to LB, means angular momentum at A is equal to angular momentum at B. If you take square, so what is that square? So that will become, if you take multiplication of these two, m square v1 v2 multiply by r1 r2. Okay, so if you take product of maximum and minimum linear speed, so that is v1 and v2. So therefore v1 and v2 is equal to L square divided by m square multiply by r1 r2. Now we have to take this product term r1 r2. So r1 r2 is equal to, since from equation 1 and 2 r1 is what, r1 is what, L divided by 1 plus e. So L divided by 1 plus e multiply by r2. R2 is what, L divided by 1 minus e. So this is nothing but L square divided by 1 minus e square, this product. Okay, now if you put this in equation 3, call this as equation 3, what you will get, v1 v2 is equal to L square m square r1 r2, which is L square. Okay, and this 1 minus e square term goes in the upward. Now, if you take r1 plus r2, which is nothing but 2a here, r1 plus r2, which is 2a. Now this is equal to, if you take r1 plus r2, so that is l divided by r1 is what, l divided by 1 plus e, plus r2 is what, l divided by 1 minus e. If you add these two, okay, so l, so that will become 2l divided by, if you do multiplication, 1 minus e square. Okay, so this 2 2 will get cancelled, and a is what, l into 1 minus e square, and r1 r2 is what, l square divided by 1 minus e square. So this is nothing but a multiplied by l. Okay, r1 r2 is nothing but a multiplied by l. So we can put a multiplied by l, because r1 plus r2 is 2a, and a is from that equation become l divided by 1 minus e square. If you put this in above equation and this in here, so instead of r1 r2, you will get l square divided by m square, and multiplication of r1 r2 is al. Now again put value of l as l square divided by mk. Okay, so using that value, what you will get, you will get v1 v2 is equal to this m square. So l square, this l square will get cancelled. Okay, so this l square get cancelled, so k divided by m into a. So call this as equation number 4. Now from Kepler's third law of planetary motion, Kepler's third law, we can say, here I have written tau square is equal to 4 pi square m divided by k into a cube. So from this equation, here we have to put k upon m. So if you take k upon m on the left hand side, so on the right hand side you will have 4 pi square a cube divided by tau square. So see, k m, if you take on the left hand side, so this tau square go to denominator, all the term remains as it is. So put in equation 4. So what you will get, v1 v2 is, instead of k upon m, you can put 4 pi square a cube divided by tau square divided by a. So again, so that will become a square. So this is nothing but 2 pi a upon tau its square. Okay, and that is required result. Now we are solving last problem, which is problem number 5. What is that? The distance between earth and sun is suddenly reduced to half of present distance. What is duration of air? So from Kepler's third law, tau square is directly proportional to a cube. Okay, so for first case, tau square, here if k is constant of proportionality, so t square is equal to k into e cube. So if t1 is present distance, okay, present periodic time, and a1 present distance, okay, so t2 is t1 upon half. Okay, so that we have given. No. So present distance is halved. So if you take a2, which is a1 divided by half, then we have to find out t2. Now from equation 1, we can write, for present distance, t1 square is equal to k into a1 cube, and for second case, t2 square is equal to k into a2 cube. So divide equation 1 and 2, you will get T1 upon T2 square is equal to, this k will get cancelled, A1 upon A2 cube. Okay, so T1 upon T2 is 3 by 2. Okay, A1 upon 2. So A1 divided by A2. If you take A1 divided by A2, this term on the right hand side, so this 2 will go over here. Okay, so A1 divided by A2 from given situation is nothing but 2 raised to 3 by 2. So if you take T2, which is equal to, okay, so T2 is equal to, this term goes to denominator, so T1 divided by 2 raised to 3 by 2. Okay, so T1 is 365 days. Present means what? In recently, duration of year is 365 days, divided by 2 raised to 3 by 2. If you solve this, you will answer is 129 days. So if present distance is reduced to half, the duration of year is 129 days. So with this, we finish our problems uh, from this chapter, from this section.